Hello everyone, it's July the 11th, another late night because I was reading about concurrency in Python. And I have done concurrency in Python in the past, but mostly through multiprocessing. But that was just, you read one or two tutorial and then you start writing it and you try it out on some toy project and it works. But this time I dug a little bit deeper, trying to understand the three different ways to do concurrency in Python. Now there is multiprocessing for sure, and there is threading, and there is async IO, which was fairly new. And you read that, and you kind of get a better idea of how they work, like which one is supposed to be suitable for what type of work. Now the reason I want to read into it because the code I have been refactoring and we're trying to kind of redesign the data pipeline. It heavily involves making the performance better, and it has a lot to do with I/O. It's basically we're writing tons and tons of data into Elasticsearch, and that kind of make things slow. And the previous version, we basically do everything synchronously, right? So it's slow as expected, but we want them to be faster. So I refactored it such that it is possible to do all the ES bound, Elasticsearch bound operations concurrently. So that's what I want to read about, how this can be done. So when you learn how it can be done, I may be able to translate the code into threading. Now, definitely we're not going to do multiprocessing because these are I/O bound. The wait all happens at I/O, so we're going to do threading. It is always better. I shouldn't say always better. It is mostly better to do it using async I/O, but doing async I/O requires significant change, like much more change to the code base. Not only the code that I'm refactoring need to use the async IO pattern, but our Elasticsearch bound code need to adapt to async IO, and it's a giant code base for that. If we want to switch it, we have to rewrite every single one of them. So I have to rewrite every single one of them. And that I'm not sure if that's the path that we want to go for, because right at the moment we are redesigning the whole pipeline. So async IO is actually not on the priority list, but I am very interested to see how async IO can speed things up even more. I mean, the toy project I ran earlier from tutorial, async IO is significantly faster. I guess just a simple HTTP requests. Synchronous calls took 9 seconds. Threading took 2 seconds. Async IO took like 0.5. I was like, oh my god, you gotta be kidding me. It's night and day. So yeah, I kind of see the point. I write async IO when you can, and write when you should, and write threading when you must. Anyway, so let's get into today's challenge. Matchsticks to squares. I remember this one. If you don't remember the solution, remember the problem. You're given an integer array, matchsticks, where matchsticks I is the length of the ith matchstick. You want to use all the matchsticks to make one square. You should not break any stick, but you can link them up, and each matchstick must be used exactly one time. Return true if you can make this square, return false otherwise. So this one is a true, this one is a false. So that's the length of 3, 3, 3, 3, 4. It's a length, so it's the fourth. Okay. 10 to the 8th. Dear Lord. Any ideas? Well, I mean, we can add them up and then see if they can be divided by 4. That could be a simple check. Oh, this one does, right? This one does. But then what? Then I don't know. Whether they can be made into a square. Well, I mean, you add them together and then you do the division. You kind of know each side, right? And then the question is it possible to find some group of the matchsticks that find 4 groups of matchstick that adds up to this value? Okay, or adds up to this value. Now what we can do, I mean, we can find a couple of checks. You add them together and you see if it can divide by 4. If it cannot be divided by 4, that's an easy edge case. If it can be divided by 4, then because each matchstick must be used exactly once, so you see the biggest. You sort the whole thing, right? You sort the whole matchstick. Oh, sorted. Jeez, 10 to the 8th. No. Oh, yes. 10 to the, wait, hold on. 15. My bad. I was like 10 to the 15. My bad. I thought we have 10 to the 8th. I was like, oh my god, how's it? It's still going to time out. No, I have 15. Oh yeah, sorted. Definitely, we sorted. And this might be brute force. Might even work. You sort it and then see the largest, right? The largest will be easier to deal with. So you go for the largest and then you see if the largest is larger than the length. Well, we don't deal with it at all. Now the largest, if it's equal to, we just keep going to the left. If it's equal to, keep going to the left. If it's not equal to, then we go to the front. We try to see if the largest and the smallest, like how, we want to know how many we need. Okay, so what are you saying? What I'm saying is, given my current one, right, and I can make choices. I can choose to use either, okay, choose to use however many I want, and then I move on, and I choose however I want, and then move on, and if it fits, we're good. If it not fit, we backtrack. So are we talking about backtracking? I think we are talking about backtracking. But how do we deal with this? So given a current one, right, it's a big one, and there are many ways to, like say 3, right? I want 1. Let's say we have a 1. And so, okay, I'll take it. And then move on. 3, I need 1. But if I have something, I need, let's say 2. And I have a single 2, and I have 2 1s. Now what do? We can either take a 2, or we can take 2 1s. I mean, I can say I'll take the smallest. I always want to go smallest first. So I take all the smallest, as many smallest as I can, and then what? You take a bit less, you take, yeah, you can say take 1, yeah, I can take one, the smallest, and then it's hard to say how. Like what there are many ways I can take, right? There are many ways I can take. And the question becomes how many ways we can take. So given an array and a target, how many different ways we can make to that. And we can say, okay, we can take one of this, so that if for each one, we can choose to take it or not take it, right? Is that like a knapsack to fit? Yeah, I think it does feel like a knapsack, right? Like how many different ways you can fit these items into multiple bags. Yeah, just think about them as full bags, and each bag has a certain amount. And how many ways we can, is there a way that we can fit everything into a bag? How do we do the knapsack? Damn, don't remember. Well, it could be like I either take it or I don't take it, right? Let's say I have a target, right? I have a target and I have an array, go from small to large. And I say, well, the first one I can either take it or I don't take it. The second I'm gonna take it or don't take it, right? And then all the way towards a certain point, and then we have a path, right? We have a path, and then eventually, when we get to the end, or when we explode, whichever goes first, we check. If it's good, then we can return a way, right? One way to do it. So we can find how many ways we can do it. Then we basically take one way, take one such a way, and yeah, we can basically say, okay, we take one such a way, and once we take one way, then we keep going. And or we have another way, and we keep going. Maybe? Maybe? I feel like very convoluted, but let's try. Let's try this. Okay, so the idea is, okay, I'm gonna say okay, s equal to sum matchsticks side shall equal to div mod s4 if not, if r return false, matchsticks are sort, right? If matchsticks last one is larger than side, return false. Okay, so that's the two. And then what we're gonna say is from this 1 by 1, right? And for each one, we're gonna find different ways that we can do. Now we pick one of them. Now we pick one and then change the state. I mean, the state can be, yeah, I can do counter. I like to do counter. Counter can be our state. Man, I can feel the capability is going down. Okay, yeah, we use a counter. And then find different ways to make. So def find ways to make. I'm going to give sticks. So I can make it every single time. What else? I have sticks and I have a target. Right. I'm going to return a list of int. Okay. And what do we do here? We need a, so from here, we're going to pass in the counter. Okay, so we can say def helper, this one be a helper. What we want is a counter. Okay, we want a counter which serves as a state. And we also want index. Okay, and then we're going to return boolean value. Right, so index. Yeah, you know index. Hold on, do we have index? We do have index. We're gonna have uniques. Okay, and then this is gonna be uniques. This one. Okay. So we'll go uniques one by one, right? So every time we're gonna say from uniques at a certain position, and then move forward and move it to a certain point, and then we do the next one. Okay, and uniques, we get this, and then we do this and do this, and once we done, and then we'll call, what do we call? If at a certain point counter is 0, right? Which means everybody has been used, then we can return. So everybody has been used and there's no error. Okay, so we say if sum counter.values is equal to 0, then we return true. Okay, otherwise we're unique, right? And then we just say I look at my index right now. Okay, so we say current is going to be unique's index, and we say if current is equal to side, right? If these two are the same, then we just return helper. There's nothing I can do. Index. Oh, hold on. If current is equal to if current equal to side, right? And counter current, we say counter current minus equal 1, and then we need to move, right? We just say while counter unique's index, while not index minus equal 1. So we need to go to the first index, first the unique value, that we have something. Now we say current equals this, and we know current, this one has something. Then we say if this is equal, right, then we just minus equal 1, and then do the same index, move on, right? If not, and it won't be larger, it will be smaller. If it's smaller than 1, right, then what do we say? We say it's not pass, this is pass counter. It'll be easier to handle, right? Then we just say candidates shall equal to self dot find ways to make when pass counter. And what's the target? Target and be side minus current. Okay, I forgot the self. Right. So we find the candidates. Right, we find the candidates. So we find the candidates, which should be a list. Actually, it's a list of lists. It could be multiple different. It could be a counter, actually. Why don't you just do a list of count? Because I believe counter we can do arithmetic on counter, if I'm not mistaken. Right, we're gonna say A equals counter 1, 2. Okay. b equals, let's say, counter 1, 2. And a minus b. Yeah, it does it for you. So I can definitely do that. A list of counter. So candidates is going to be a list of counter. Then we can just say for CC in this list of counter, what do we do? Oh, okay, we add it back. Say C equals a minus b. I can do this, yes. So for this, and then we just say helper index again, but counter is going to be the current counter minus CC, a new counter. All right, and then we say if this is good, we'll return true. Otherwise, they go up. Try the next one, try the next one, until the last. If nothing works, return false. Okay, so now we just need to do this. Given a counter of all the values, we want to find target. How do we do that? Because we don't have that many, I can expand the counter into a list, right? We can expand the counter into a list. And what I'm thinking is maybe we don't need to expand the counter into a list. We give the uniques of the counter, right? And then for each one, we decide if we take one. Nah, I don't like it. I don't like it. Let's get the list. Let's get the sticks. So equal to for key value in counter dot items, right? And what we do is going to be this times value. Not sure. Oh, I have to try. Okay, so b equals this, right? We can say, let's try, see if this one works. Kind of a deconstruct. We don't have counter, but we have b. Iterable unpacking cannot be. Do we have like flat map? Reduce. It's too complicated. There is a way. There is a way. But seriously, how do you flat map? I think I'd searched this one before. I can't believe I forgot. I definitely searched this one before. But when I use a PySpark, we just use regular. Oh, okay. So we have to do multiple. I guess it's fine. It's okay. This was the first level, and then for this in range V, right? Oopsie doozy, what the heck are you doing? Okay. So that's all the sticks. And it doesn't matter, we don't have to sort it. And we just say def knapsack. Is that how you spell knapsack? We have a index. We have a target. Okay. We then return nothing. Result equal to this. Okay, so for this one, what are we going to do? We're going to say for each index we either do it or we don't do it, right? So we have a current target, and when target is equal to 0, right? We say if target is equal to 0, and path nap. It's going to be a list of int, right? And then we just say if it's and then rest dot append. We can go counter nap. That's it. Else down a current. Now we either do it or we don't do it. And now we say else we either do it if target is smaller than 0, right? Then we just return. Although we don't even have to consider when you say else target is larger than 0, right? Target larger than 0, there's a chance we can do the current one, and we simply say take the current, right? Just say knapsack index plus 1 target minus sticks index, and then nap plus sticks index. Yeah, let's just say nap dot pen sticks index. I'll do this, and then nap dot pop, and then don't take the current one. Do not take current one. So we're done. Then that's it. And then we call knapsack. Start with 0. Target is target, and then nap starting with this, and we're gonna return the rest. Okay. So helper. We're gonna call helper index. We start with 0. We start with counter, and I'm going to return this. All right, let's see if this convoluted thing works. This that should be true. And this shall be false. It just sticks. Make square. Run it. Error. Oh, for sure. If it's this, if it's this, and index is smaller than sticks. Otherwise, that's a fail. Oh, that works for this one. Do we dare? We do, but we can. What the hell are you doing, man? I don't know. That's definitely impossible. You should put something that is possible to see if it's. Let's try it. Aye. So long. The heck? I got a wrong answer. What? Come on, man. It's supposed to be true, but my response is false. Oh, and I take a long time to get a result. It's supposed to be true. Huh? Let's see. $12, right? We can take 5. And when we take 5, we have different ways to make 7. We actually only have one way to make 7. Current, counter, and CC. Let's see. Yeah, I don't need this. Current. Wait, aren't we supposed to sort it? Oh, shoot. Reverse. Still not right. Oh, shoot. I forgot to. The CC itself will find ways to make counter. Counter, I need to delete the 5. You see, the 5 never go down. So counter current minus equal 1. Then we do this, right? And then backtrack plus equal 1. There we go. There we go. We missed a few lines of code. Okay. All right, try again. 走你. All right. Not too bad. I feel very convoluted, but I can't. Oh my god, come on, man. Yeah, I was trying to have a little conversation with my father right now. And then, and switching different input. All right, so my current solution is very convoluted. We use a backtrack for the main solver and a knapsack for a helping solver. Right. The main solver goes from the largest stick to the smallest, and for each stick we find how many more lengths are needed to make a side. Then we can actually do it here. Yeah, that's what I'm supposed to do. I'm supposed to do this no matter what. I should do it here. Current equal to this, and then if this, we keep going. Otherwise, we don't have to do this. Yeah, that's how it's supposed to be done. That's fine. We can just keep writing, right? Then we use knapsack to find different ways of using smaller sticks to make, right? To make the sides. Maybe sorting can help. I don't know. Yeah, let me sort. We use knapsack to find different ways of using smaller sticks to make the difference. Then we try each way to see whether the main solver can return true. If none of the ways lead to a true, return false. Yeah, I don't know the runtime. It's like 2 to the n. Yeah, we call it 2 to the n. It's definitely not these two solutions. We're going to see like what I did last time, and see this time, and see this time, and see this time. Oh man, I can't even try to run this again. Same method, but make small modifications. Just tiny little bit of modifications. I don't think it can make any difference, but let's see. Okay, add a sort. Hopefully, like this part can be faster. It's the same. It's the same. Okay, so this is the original one, 173. I just full backtrack. Yeah, it's not the ones that we're looking for. So 195, we have more test cases this time. A lot more test cases this time. And oh, that was a different one. 173, 195. Yeah, so we have a lot more test cases. It's okay. All right, so this is the backtracking with memorization. Bitmap. Ah, I noticed the bitmap, I didn't notice this time. So it's DP on a subset, so we keep track on which one you used. So what do you mean on which one you use? Oh, you use these, you use this. So hold on. So what's the process? We have a bitmask as the state, and then you can say we'll pick the first one. We do the regular check, right? And then we say pick this one, and then we need to pick some to form one side, right? So we pick whichever to form one side. Once we're done, right? So we pick one side. Once we're done, then we try to pick so it's the current state, and then we will do the second side, do the third side, and we do the fourth sides. Is that how it's going? So for each time we have a state, we just go through the state to see if we can find I think I kind of know, but I need to write it. Yeah, 15 is very suspicious to be bitmask. So it should be DP with bitmask. Okay. So we say, now we say we have all this max larger than this, larger than side, turn false. Okay. So now def dp, right, we're gonna say state is gonna be actually an integer. And we have state, we have num sides complete as an integer, and the target as an integer, right? And I'll return a Boolean value. Okay. So when we pass in is the original state, right? Number of sides complete is Yeah, I don't know if I should call it DP. I will just call it helper. So I try to fulfill the target. Okay, I'm going to say if num size complete equals 3, then we just return true. Right. Otherwise, we have a target. So we either take it, we don't decide the current state, we either take it, not take it, take it, not take it, right? If we take it, then we produce the next state, right? And we say if target is equal to 0, then helper, then we return helper current state. I don't have to. I can say if target is equal to 0, target equal to side, and num size plus equal 1. And then, okay? So we do that. And then we just go one by one for I in range, because we have 15. I have 15 values. So I just left shift. $16, right? Actually 15. Well, 15 times. Say if one left shift I and state. If it's 1, that means this one has not been taken, right? So now we take it, right? Now we take it. And I just realized I think I should go the other way back from 14. Because it doesn't matter. So we shift that, check that one, we say, okay, if this is 1, that means I can choose to take it. Right? We choose to take it or not take it. So if we choose to take it, then we say we can go exclusive OR, right? So we say helper state exclusive OR 1 left shift I, and size complete, I don't know, but target minus match sticks I, right? And we say if this is true, then we return true. Otherwise, try it again, try it again, try it again, try it again. And then if everything tried, then we return false. And yes, I'm gonna cache it. Oh, this is actually a very good problem. Always for max size, man. We have that experience, very bad experience. And now we can just call helper state is just going to be one left shift. Oh, n equals a len matchstick. Right? So this is not 14. This is n. And this is 1. 1 left shift n minus 1. Right? Left shift this minus 1. So everything is available. None as complete, colon as no. Target is going to be side. And we're going to return this. Okay. Let's try solution 2. Oh, yeah, this is right. Let's see. See if it's any faster. Uh-oh. What? What? You gotta be kidding me. $3,000. No way. What did I do wrong? We check the trivial case. We do this, backtracking current side, which I have, which is our target, side completed, and the state. If this is 0, this plus equal 1. If side equal to 3, or backtrack side completed, state. Oh, as this, I don't take the current one. Wait, hold on. What is that? Otherwise return false. If current side is 0. Okay, if current side is 0. So side is not 3. Then I will do this is basically just do this one more time. That's why I don't do it, because it's fine. All right, so this is a big difference. 0. Honestly, it's fine. It's the same code. Okay, no, it's not exactly the same. If state and match 6i smaller equal to current side. Okay, so that's the only thing that I did back then, and I didn't do it now. I don't have current side, I just target. Wait. Oh, this might be because additional check. It could be. It could be. Like kind of wasting, but it's fine because this one will become negative, right? The target will be negative. If it's 0, if it's negative, then we return. You know what? This is, yeah, we did a lot of things that's unnecessary. I see. Okay, so try one more time. Yeah, has this smaller. Let's run this one again. Okay. Yep, that's more likely. Yeah, there should be n. Okay. Now we have a slightly better solution. It's a lot more complicated. All right, that will be it. That's a good problem, right? It's a very good problem. Let's see. I think that's the official solution. DFS. DP. Yeah, 3 sides. All right, now I don't have any intention to read. I'll stop right here. Yeah, this is not an easy one, but it's a good one. I'll see you guys tomorrow. Adios.